lecture, we will address the final steps for sizing a photovoltaic standalone system. After a brief deepening on the load definition, you are going to address the battery and the photovoltaic panel designs. The first step still concerns a load analysis, particularly its consumption and its typology. In the last lesson, the loads of the system were identified and classified as normal or critical. Furthermore, according to the IEEE Standard 1013 of 2019, the days of autonomy required by our system were also quantified. Now, we need to return to the load in more detail, finding the datasheets of the expected utilities. If historical data is not available, you can simply search on the internet to obtain some reference values. For example, a traditional microwave oven could require an instantaneous power of 1 kW, which implies a current of 4.34 ampere at 230 volt. In this case, the microwave oven is a device that can be expected to run for 15 minutes a day. On the contrary, 500 watts of lamps is a lower instantaneous consumption, but could be required for several hours during a day. These distinctions are important to calculate the three key parameters that identify the type of battery pack to be installed: battery capacity, maximum discharge current, and maximum charge current. The battery capacity can be calculated based on the overall power needed by the system and the expected days of autonomy. To this aim, the total expected consumption per day in kilowatt per hour is multiplied by a constant equivalent to the required days of autonomy. Then, the obtained value must be divided by a foreseen battery voltage level. The result is the battery capacity needed to be installed. Other constraints, such as the minimum battery charge level, must be accounted for because they can impact on the actual days of autonomy. Once the battery capacity is obtained, market research has to be performed to select the most suitable battery. Regardless of what you decide to do, you will always need to identify two additional parameters, namely the maximum discharge and charge currents. These, respectively, determine the maximum output current provided by the battery to the load and the maximum input current accepted by the battery from the photovoltaic plant. The first one must be greater than or equal to the maximum current required by the loads. The second, instead, must be multiplied by the charging voltage of the battery. The result must be compared to the instantaneous power that is required by the load. In fact, if it is lower, the battery will drain faster than it recharges. The maximum discharge current can also be affected by other factors, such as depth of discharge, which results from the choice of a particular cell type, and it may impose a limit on the actual maximum discharge current to maximize the life of the battery pack. Once that the battery is determined, the system capability must be sized. Obviously, the system should be able to supply the load, but it is preferable to recharge the battery faster than it drains. In this regard, it is necessary to select the most appropriate array-to-load value. This parameter is defined as the ratio between the system power capability and the required power by the load. This value is also influenced by the previously selected battery, since, in the presence of large capacities, increasing the array-to-load to recharge the battery pack faster could be useful. This can decrease the risk of damage caused by an operating condition below the battery optimal state of charge. According to the IEEE Standard 1562 of 2021, for normal loads or for highly irradiated areas, an array-to-load ratio of 1.1 or 1.2 is sufficient, while for critical loads or for low irradiated areas, typically it can go up to 1.4. Once the power to be delivered is known, it must be adjusted to compensate for the expected losses in the system. In this regard, an index called Specific Photovoltaic Power Output comes to our aid. It is estimated by several online weather database platforms, such as Global Solar Atlas, and considers losses due to the air temperature and assumed system configuration, shading, soiling, and topographic and land use constraints. This index must be increased by the expected losses on the system due to the passive and active electrical components. In case of no regard of this type of losses, it is possible to consider a given percentage between 2% and 10% as additional to the array to load ratio. Finally, the system layout and the structure of the panel can be defined. Let's proceed by points. The photovoltaic system must always be associated to a DC-DC converter with a maximum power point tracking algorithm that stabilizes the operating point and maximizes its efficiency. The converter must be accompanied by a charge controller so that the battery is not damaged during recharges. It is necessary to identify the type of utilities. If it is going to be powered in alternating current, it will be necessary to insert a DC-AC converter interface. This device must be sized to be able to sustain the required power and to be supplied by the DC voltage level of the battery and the system. All these aspects impose constraints on the system size, and you may need to retrace your steps to be sure that everything is compatible and appropriately selected. Once the electrical scheme is defined, only the structure of the generation system is missing. The system can consist of one or more panels, and each panel is composed by a certain combination of strings connected in parallel, and each string is composed by several photovoltaic cells connected in series. The voltage achievable by the panel is directly proportional to the length of the string, while the deliverable current is as higher as greater is the number of strings in parallel. Therefore, the combination of series and parallel cells determines the power of the panel, whose efficiency is closely linked to the quality of the material by which the individual cell is composed. The best performing cell for this kind of applications is the monocrystalline silicon one, but there are also other types if you prefer a cheaper solution. However, when selecting or designing the panel, its derating factors must also be considered, as the ambient temperature can significantly affect its energy production. As a reference, consider that all the nominal values from datasheets are calculated at a temperature of 25 degrees, according to the standard test condition. Therefore, an area subjected to very high temperatures has a lower production potential than an area with temperature closer to the standard. The sensitivity of a panel to the changes is defined by the thermal derivatives coefficients for current and voltage, provided by the manufacturer on a datasheet. We have now addressed all the key concepts to fully design a photovoltaic standalone system. To briefly recall all the steps required for a correct sizing of a photovoltaic system with electrical storage, you have to research on the geographical location along with area and soil details, retrieve meteorological data of that precise location, assume a type of user and only appliances to be supplied, generate a load profile and classify possible critical loads to define the maximum autonomy of the system, carefully choose a suitable battery pack, compute the required power by the photovoltaic plant adjusted by the array to load ratio and by forecasted losses, design the plant layout, choosing the needed electronic devices and selecting the panels to complete your system.